All right, this topic is the Mram, and remember the M stands for midpoint. So find the area bounded by the curve x squared plus 1 on 1 comma 3 with 4 subintervals. Well, the height of our rectangle is actually decided by the y value that's in between these two. So if you go up from this point, the middle, that's going to be the height of your rectangle. Same thing here. What's in the middle? 1.5 and 2.0. Well, that's 1.75, but we go all the way up, and that's there. All right, so what is this x value right here? It's a 1.25. This one here is a 1.75. This one here would be a 2.25, and this one here would be a 2.75. And again, you are using the height of those x values that are right in the middle. So you're using that height. Keep going up. You're using that height. All right, so how do we find the width? Well, the width is still the same way. We're going to do 3 minus 1 divided by 4, which gives me 0.5. And you can even see here that our width is still that 0.5. But this time, we're going to have 0.5 times f of 1.25 plus 0.5 times f of 1.75 plus 0.5 times f of 2.25 plus 0.5 times f of 2.75. So let's go ahead and let's find that in the calculator. All right, so plugging 1.25 into here, I get the 2.56. Plugging this into x squared, I get this, and so on. All right, and then just plugging that all into my calculator, I get 10.62 units squared. And that would be my estimate of the area under the curve using Mram. You might notice that that's in between the LRAM and the RRAM, which is, fairly common, but does it mean that it's the most accurate? I don't know. Well, what do you think? The area under the curve is estimated by drawing rectangles under the curve. Which method below looks like it will be the most accurate? Which is definitely an overestimate? Which one is definitely an underestimate? Well, you can see that in the LRAM, in this case, because our function is increasing and concave up, this is actually an underestimate. You can see all this open space that our rectangles didn't count. The RRAM is actually an overestimate because it's counting all this stuff that actually is not even under the curve, so that's an overestimate. The Mram, I'm not really sure if it's an over or an under. That's a good question. Although we could establish rules to determine whether a left or a right Riemann sum for an increasing or decreasing function will overestimate or underestimate the actual area, it actually is much more helpful to use a sketch of a graph to reach a conclusion. Alert, alert, assumption alert. Students often mistakenly believe that this balance, the Mram, is perfect and that the Mram is exact. In other words, some people think that the Mram is an average or in the middle of the LRAM and the RRAM. This is not true. This is not true. All right. You are entitled to your opinion, but you are wrong. Which one is actually the best? What if I told you it depends? All right, it really depends on what your function looks like. There actually is an answer to that. What is the best way to estimate the area under the curve? Well, using literally an infinite number of rectangles. Okay, so here we have 1,000 rectangles, which seems pretty exact, but it's not exactly. So we will soon talk about how we can do an infinite number of rectangles. Pretty exciting. All right, thanks for watching. Bye-bye.